Bismillahirrahmanirrahim. Greetings. Composition of functions appears in the curriculum of basic algebra, college algebra, and also pre-calculus. Now, the chain rule, which is possibly one of the most extensively used in differentiation, is based on composition of function. And one reason is that every function, almost every function, is a composite of other functions. In other words, every function can be written as a composition of other functions. Now, I have already uploaded a complete lecture, in a sense, about the concept of function, and also about 3 or 4 other videos about the inverse functions. So you can find them in the list of my videos in my channel. But in this video lecture, I'm going to review that, so I'm not going to go too deep into the subject. But and as a kind of preliminary, as a kind of preparation for the next video, next lecture. And in the next lecture, I'm going to only concentrate on the composition of functions, the concept of composition of functions. And then I also intend to upload 1 or 2 lectures about the proof of chain rule for the freshman calculus students. Okay, then enough for introduction. Let's get started, shall we? Now, we refer to the concept of function in 2 ways. One of them is through the formal mathematical definition of function, and second one, function as a subset of relation. As a matter of fact, it's better to say a proper subset of relation. So let's go over the former before we discuss the latter one. Now, function is a rule of correspondence between 2 non-empty sets. They are known as domain and range. I will come to that with an example. Such that each element from the domain set is uniquely paired with an element from the range set. Notice that each and also uniquely and these 3 words I emphasized 3 times, because in order to fully comprehend the concept of function, we must know these 3 words play extremely important role in fully comprehending the concept of function. Now, each means every and all. So every and all elements of the domain must be used. We come back to that. And then uniqueness, as the literal meaning of the word indicates, each of those elements in the domain must be used uniquely. Again, when I go to an example, this becomes more concrete. And then the word "and" means at least one. And that brings about different kind of functions. The word "and" brings up that different kind of function. And we have into function, we have onto function, we have one-to-one function, we have one-to-one and one-to-one correspondence function. There are some fancy names for them also, injective, bijective, surjective, that I may mention when we go, when we apply some examples. Now, I go to demonstrate the idea through a schematic diagram. Now, a schematic diagram that I have drawn here is not a plain darts, is not a game. This improves our conceptual understanding of the subject. So take them seriously, it's not kind of a fun or playing game. Now here, this is the set of my domain. and consists of all the values that the independent variable can possess. As a matter of fact, that is the definition of domain. Domain is what? Is the set of all permissible values that the independent variable can possess. Now, for example, I have in the next one, I have an example to say, to indicate about that one when I go to that one more time. Now, then a function is the rule that in 2D pairs each element of the domain with an element in the range. So that word "and," the f indicates, the function indicates what will be that element. So that element, that's what they call it, the elements in the domain, we call it independent variables. Because the elements in the domain can be selected randomly, but the elements in the range cannot. The elements of the range must follow what the rule is imposed on them, what the f tells what should be paired with the elements that in the domain we have selected. So a schematic diagram very nicely explains that situation, what the concept is all about. Do you follow me? Now, the cardinality of a set means the number of elements in that set. Now, as I have already written, the cardinality of the set of range can be either less than the cardinality of the set of domain, or can be equal to the cardinality of domain, or can be greater than cardinality of domain. So the number of elements in the domain can be either less than the number of elements in the range, or can be, or vice versa. Let me say it about the range. The elements in the range can be less than the elements of the domain, can be equal to the number of elements in the domain, and can be what? Can be greater than that. Of course, when we talk about the infinite set, if they are not countable infinite set, this greater than or equal kind of, we have to know it intuitively in a sense. We cannot say, because there is no such a thing, one infinity is bigger than another. Infinity is another subject to talk about. I'm very interested. So this about that one. Now let me go and a little bit further discuss the domain and range, if I may. Now, now suppose that the domain of a function is, this is my function, I haven't defined the notation yet, I'm going to come to that, is equal to 1 over x squared. It's all real numbers except 0, because it's all permissible values that independent variable can possess, and here 0 is not permitted, x is not permitted to assume the value of 0 because we get division by 0. So the domain is all real numbers except 0. Now I said that the range is R, which is all real numbers, all right? Then with respect to this rule of correspondence, almost half, intuitively speaking, almost half of the range are not going to be used, because f is going to take elements from the domain, and the range according to this rule of correspondence is going to be all positive real numbers. You see that? These all are positive real numbers. So then what happens to the negative real numbers? They remain same. We don't bother them. And they do not violate the definition of function. So in a sense, half of the elements of the range has been used in this notation that I wrote. Now I change and I say f is from real except 0 to positive real. I do mention it. So when I mention it, then this becomes an onto function. Previously was into, now becomes onto function. And onto, another name for that is surjective the mapping, they call it. It's just a little bit fancy word for that. So they are good to realize from where to where they are swinging, so that you notice the domain and range of that. Okay, now let me go to the notation. I have written them large enough so that I don't have to go and zoom it in and out. Now here, the notation is a suggestive notation. By the way, let me say a few words about this concept of notation. Leibniz, a German mathematician who was contemporary with Newton at the time of Newton, he was known of spending sometimes days seeking for the notation that contribute to the concept. Seeking for a notation that contribute to the concept. Now, for instance, for those students who may be taking freshman calculus, the notation dy over dx is a notation that was selected by Leibniz and has contributed a lot to the concept of the derivative. That, of course, I'm not going to go over that, that's outside the subject. But this notation, I believe, I don't know the history behind that, I have a little bit investigated, but I have a strong feeling that this notation is also possibly selected, adapted by Leibniz. And that is suggestive notation. Now look at that. The x is an element from the independent, is an independent variable, represents an independent variable, is an element, if we put that, from the set of domain. So x represents each and all elements in the set of domain. And then f is the rule that tells what element should be paired with x. The rule, so it says what element in the range should be paired with, in 2D of course, should be paired with the selected element value in the domain. So this is the rule. And the elements, the element that is selected in the range to be paired with x is f of x. You follow me? So f of x is an element in the range. That is, root f tells that element should be paired with x. Now there are other benefits of this notation that I have put them in writing for you that I go over. They are very kind of elementary but very kind of tricky in a sense, and is very important especially for the beginner students to fully comprehend them. Now here other benefits are written that other benefits of the notation f of x. Now when I say f of z, purposely I didn't put x, not to get confused. When I say f of z equal to z squared plus w, now here I know that in this equation, in this expression, the z represents the independent variable. So it is z that can assume different values. It is z that we can impose or assume different values for that. And in that case, w often stands for constant, remains the same for the entire argument until we change that one and go to the next. If you are familiar with the parabola, for example, x squared, then x squared plus 3 is the same parabola but 3 units up. 3 remains same, but x start to assume different values. Then we can say, for example, f of x equal to x squared plus 7. So the graph of parabola is moved up 7 units. So that 7 is the constant, remains same, but x start to assume different values. So now if I write y equal to z squared plus w, then there is a little bit confusion. Which one of them is the independent variable? Because they both are symbols. Which one of them are going to assume different values? Is it z or is it w? Then in that case, we have to emphasize. But in this case, we do not have to emphasize. Now that is one advantage. The second advantage is also when we have, for example, I made an example, I have 3x squared plus 7. Now, what is f of, let's say, rectangle? and inside rectangle, let's say there is a long polynomial. Then what you do, 3, 2, plus 7, all of them remain same. The only thing is that you drill a hole about the x, you use jigsaw, cut it off, and replace it with the rectangle which was in the stomach of the f. Do you follow me? So when we put that one, will become 3 rectangle square plus 7. You see, 3 and 2 and plus and 7, all of them, they didn't change. The only thing that we replaced was x. That is another beautiful advantage of this notation. Now I made an example, for instance, if f of x equal to 3x squared plus 7, then f of x plus 1 is 3x plus 1 squared plus 7. That's another beautiful advantage of this notation that contribute to the concept. Do you follow me? Okay, now I think I have said enough about the background preparation. I'm using all of them because of the composition of functions and also about the proof that I have to mention about the chain rule so that you have enough background. Now, again, this is kind of review. This is preliminary for the coming lecture. So if you want more detail about the concept of function, please, I'm repeating myself for the second time, go to the list of my videos and you will find them over there. Okay, now let's go to the latter one, the second reference to the function in a sense. Now I have written. So first, I said the function is a proper subset of relation. So first we have to know what is a relation, because the word relation is used in the description of the function as a proper subset. Now relation between two sets, two non-empty sets, A and B, is what, as I have written, is the set of all possible ordered pairs A, B, such that A comes from the set A and B comes from the set B. So a small a is coming from the capital A set A, and a small b comes from the capital set B. All possibilities. Now, I made an example so that you can see that. For instance, if A consists of 3 elements, 1, 2, 3. 1, 2, 3 doesn't mean 3 numbers. It's just we know them, the name of them is 1, 2, 3, so I named them. You can call it Nancy, Robert, and Jack. Any other name, or you can use maybe elements from the periodic table. So these are 3 elements, and then B consists of 2 elements, A and B. So the relation will be this set, which means according to this definition will be what? Will be 1A, 1B, 2A, 2B, 3A, 3B. So you notice that this A has 3 elements and B has 2 elements, then A cross B, as a matter of fact, that is the way we call them. We use the word A cross B, and also we use the notation of absolute value for the cardinality to a small line segment parallel. This is kind of a standard, most of the textbook they use it. So A cross B, which is the relation, consists of 3 times 2, 6 elements. So we can generalize this idea and say if the set A has, let's say, m elements, and the set B has n elements, they are finite, then the relation A cross B will have m times n elements in that. And also we notice here, this is just observation, that A cross B is different than B cross A. Because B cross A will be what? B is AB, so will be A1, A2, A3, then B1, B2, B3. Again, 6 elements, but those elements, the order is different. So A cross B in general is different than B cross A. Now, What I just said, I have put them in writing for you if you wish to write, to take a notes, because the students that they like to take notes. And now again, this notation that looks like absolute value is used for the cardinality, and also used in this case I'm using as a cardinality, which means the number of elements in that set. So I have already mentioned that if A has m, let's say it this way: if a cardinality of A cross B is m, there are m elements in the previous example. A cross B has 6 elements. Then 2 to the m, which is 2 to the 6, which is 2 to the 3 times 2 to the 3, which is what 8 times 8, 64 different subsets we can construct, we can drive out of it. Do you follow me? And then some of those subsets are, they satisfy the definition of function, some of them they do not. How many of them they satisfy, that is the subject of combinatorics, that is outside the discussion of this subject, but it does mention yes. Now, for instance, here, this relation, look at that. 1A, 2A, 3A, where A is 1, 2, 3 as a domain of my relation, and the range was A and B. Now, this B is not used. So this is a nice looking function, but with respect to A to be 1, 2, 3 as a domain, and B to be AB as a range, this is called an into function, because not all the elements in the range is used. Now, this also, look at this one. 2 is paired with B, 1 is paired with A, and 3 is paired with B. This is all the elements of the domain are used, and they are used uniquely, as you notice that one. They are all unique. 2 is paired with B, 2 is not paired with anything else. Same is true with 1 and 3. So therefore this satisfies the definition of function, and this represents an into function. Excuse me, I said into, is an onto function, because all the elements in the range have been used. There is nothing left over. Do you follow me? Now look at this subset, this particular subset. 1 paired with A, 2 paired with B, 3 paired with A again, and 1 is paired with B. Here it is, one element is violating the definition of function, because 1 is not uniquely paired. As a matter of fact, the word uniquely also implies that all the elements in the domain should be used. Because when it says uniquely, if there is any element left in the domain, we are not sure if that honor the definition of function. How do you know that the element that is left over is not going to violate the definition of function? So the word uniquely also implies that all the elements in the domain should be used. All right? It's the deductive thinking, think and reflect. Okay, now this definition, this will not be function. Now let me go as a final representation as the familiar circle that we are very familiar. We have seen them from junior high school, and that is x squared plus y squared equals to r squared. In this example is x squared plus y squared equals to 25. So in junior high, in high school, we go that with a vertical line test we use to find out if the graph is a graph of a function or not. And that is in case if we do have access to the geometry, if we have sketched the graph. But what about if you are in an analytical situation that we don't have the graph on that? So I made an example as a kind of a schematic diagram and in a sense analytical interpretation. And the domain of my function is of the relation of the circle, not function, excuse me, the domain of that is from -5 to 5 inclusively, all right? And then all the elements except the endpoint, except 0 and both sides, then every element from -5 to 5, from negative to 5, they are paired with two elements in the range. Because the range of that consists of these two. You see that? So every element I select is paired with two elements. Therefore, the relation is not the relation of the equation of circle does not represent a function, but represents a relation. But two explicit functions can be derived from that. And each one of them, for example, is negative square root of 25 minus x squared. The other one is positive 25 minus x squared. And that is not the case with every relation. Many relations, in fact, most of them we cannot separate x and y's, unfortunately, in a sense. Okay, then, I hope that this video was beneficial to you. As I said in the introductory, next video I'm going to talk about composition of functions, and then again 1 or 2 lectures about the proof of chain rule. Okay, then for the second time, I thank you for watching, and as always, I wish you prosperity and good health, and please stay safe. So long.